Welcome to the final stats lecture of the course. This hopefully will be fairly straightforward to you since it builds on everything we've done already, and it's actually the same thing as something we've already done. Now the topic for today is called one-way ANOVA. Now this is another way of creating a model for your data. So let's take a step back for a moment and let's remember why we create a model and what the model is supposed to do. Our ultimate question that we're trying to answer when we look at our sample data is how can I explain as much variation in my data as possible? Now, total variation is a number that you calculate, and the goal is to explain as much as you can with the model, and that's the R squared number. So the second more specific question is what model can I create to explain the most variation? And that's what your hypothesis is trying to show. Now, this process of one-way ANOVA is actually nothing new. It is almost identical to the linear regression for continuous variables. We just do it in a different way. So I'm going to show you that procedure of how we go about doing it. But we have to understand some concepts first. And you'll see the connection in the relation to the linear regression as we go along. Firstly, why use one-way ANOVA instead of linear regression? Well, the answer is that you can use linear regression instead of one-way ANOVA. It's just another way of getting to the same result. You can do both. But one-way ANOVA is something that you can only use when your independent variables are categorical. So in the case that you have categorical independent variables, that means not continuous, then you can use this. So we're going to look at this using some data here. So now here I'm showing you teacher ratings. Now these are not ratings of teachers, these are ratings from teachers about their students. So each one of these numbers is a different student, and it's an average teacher rating on how social they think these students are. Now, there's no model here. This is just the teacher rating. So we want to build a model around these teacher ratings of the students' social abilities. And we're going to say our idea is that whether or not the students involved in extracurriculars determines how the teacher views them from a social perspective. So even though they might only have them during class time, the number or the kind of extracurriculars they're involved in would impact their perception of how social the student is. So we're going to assign three groups to the students here. We're going to have students that have no extracurriculars, students that have extracurriculars that are non-physical, and students that play sports, things that are physical. And we're going to assign those students to those groups. And so we're going to just for time being, we're going to title them Group 1, Group 2, and Group 3. So Group 1, no curriculars, Group 2, non-physical, and Group 3, sports. And we've got 5 for each one of those. Now, in order to understand the concept of one-way ANOVA, we need to plot this and look at the chart of how all this data lines up. Now here we have our data plotted, and you'll see that everything's broken out into the three groups. We have the groups 1, 2, and 3 on the bottom, and on the side we have our teacher ratings. Now note that the teacher rating goes from 0 to 7, 7 being the highest possible rating on the scale. Now in one-way ANOVA, we have different kinds of means, so we have to give them special names. And the first kind of mean we have is the one you're most familiar with. We call that the grand mean. So the grand mean is the average of all your data. So you just take all these 15 data points from all the groups, you add them together and you divide by the total, and that's your average, just the normal mean that you get. But in one-way ANOVA, we have another kind of mean, and it's called the group mean. And the group mean is just the average of only the data points for each group. So in each case, you just add up the 5 data points from the group, and you divide by that total instead. So it's like a sub-mean in a sense. And what we're going to do now is we're going to look at each one of these means and see what that actually means in the context of one-way ANOVA. So let's do that now. Now when we work with the grand mean, we can use that to find the total variation. That's the same as the SST, or it was the SST, total variation. Now remember that total variation is just everything that's away from the mean of the data that determines our variation. So the closer everything is to the grand mean, the less variation you have, and the further away it is, the greater the variation. So the way we determine our total variation is the same way we did before. We just take those deviations, we take the grand mean, and we subtract off the data point, or excuse me, the data point minus the grand mean to get our deviations. Now note here that I'm calling the grand mean, I'm using the notation a capital Y with a bar over top of it for the grand mean because we have different kinds of means here. So in the symbols, we have to specify which one we're talking about. So we're going to use a capital Y with a bar over it for the grand mean. And we're going to use something else for the group means. So here, you just take each data point minus the grand mean, and that'll give us our deviations. Now we want variation, which is about squaring it. Remember, because we want to get rid of all those negative terms that are going to cancel out. So our final formula is the same as what it was in linear regression. We have yn minus capital Y bar, that quantity squared, and we do that for everything in the data sample. So nt, I'm specifying nt as being the total number in the entire data sample. So from 1 to, in this case, 15. And that's just our total variation. So that gives us our what in linear regression would be the SST. Here we just call it total variation. Let's look at the next way that we calculate stuff out, or the next part of it, which you can imagine is going to be the SSE and the SSR. So let's take a look at that. Now you're going to learn how to calculate out what's called the between group variation. Now between group variation in one-way ANOVA is the same as SSE, or that's sum of squares of your estimate. That's what your model does explain. How much of the variation is explainable by your model? And that's what we're looking at. Now hopefully you can see why this is the explainable part in a second when I draw these lines. The way you calculate out your between group variation is you take the group mean minus the grand mean. So we're going to take just the deviations from these three groups, group 1, group 2, and group 3, and subtract them from the grand mean. So how far is the group mean deviate from the grand mean? That's what we're looking at. Now here, I've titled the group means as lowercase y bar with a g. And the g could be, and g in this case could equal 1, 2, or 3 in this case. So we're doing this lowercase y as being the group means here. Now when you calculate out these deviations, this tells us, okay, if I'm saying that the groups that people are assigned to is what's determining the variation in the data, and I'm calculating out this number, that's telling us how much our model does explain. And the way we calculate out the variation of that, or how much variation that explains, is by taking those deviations and squaring them. So we're going to have, right here, you're going to see we have this same deviation, the group mean minus the grand mean squared. That gives us our variation. And we take that from group 1 up to however many groups we have. In this case, it's 3 groups. Now you'll notice here that there's another term in front here, though. We've got this NG. So that's the number of items that are in each group. So that's going to be dependent on which group. In this case, it's easy. We don't have to worry about it because we have 5 people in each group. That's an even spread. But you can imagine cases where you're going to have data that maybe you've got 10 people in one group, 5 people in another group, and 6 people in another group. Well, then those weightings are not the same. And so what this term here is, this gives weight. And hopefully you understand what I mean by weight in this case when you're doing an average, a weighted average. All right, so that weights that term in the variation so that way it's representative of how much data is in each group. All right, so that's how you calculate out your between group variation. Now, that's the SSE. We've looked at the SST part of it. So the last one that correlates with the SSR, with the linear regression, is going to be the SSR. So let's take a look at that. Now, the within group variation, that is the same as the SSR. That is what your model does not explain in your data. So your between group variation is what is explained, and your within group variation is what is not explained. And you're going to see that in a second here. So that's what's left over. So if I'm saying the groups are what explain the variation in the data, then the variation within each group is going to be the part I still can't explain. So why is there difference within the groups themselves? And so the way we calculate that is then going to be the data point within each group minus that group mean. So here now, just for notation, you'll see here I did a y of gn. So that's the y of just that group for all the numbers in that group. All right, so again, this is just the data point. This is the data point for that group. So this is a data point, but only for that group. So you take those 5 and you subtract them from the group mean, and that gives us those deviations that are left over. So if I were to write this out to get the variation in total form in a strict mathematical sense, we would have this. So again, you'll see the same, it's deviation squared like we normally have, and we go from n equal 1 to n sub g, which is just the number of elements in each group. Now I have a second sum here because you don't just do it for one group, you do it for all 3. So you go from group 1 up to group 3. So this, in this case, this would be 3, and this would be n for all of them would be 5, even though in another case you might have different groups or different group sizes. So that's what we'd be doing here, is you just find that the variation within each group, and you add it together, and that's your residual. That's the same as the SSR. So now let's go back to the actual data again and take a look at those numbers in those columns. Now here we have our teacher ratings and our groups assigned. And the first thing we need to do, we're going to go through this just the same way we did with the linear regression. We're going to create these columns and we're going to add them together to get the variations. So the first thing we do is calculate out our group means. And here are our individual group means for each 5 data points. So you'll notice here, these 5 are all the same, these 5 are the same, and these 5 are the same. Now, to get our within group variation, that's the part that we cannot explain, the leftover residual part that we can't explain with our model. We're just going to take our teacher rating and we subtract the group mean from that. And that's going to give us this number, and then we square it also. So this, and then we square it, and that gives us our within variation here on the side. And then we sum that all up, and we've got a total within group variation of 6.02. All right, so that's our first number. That's equivalent to our SSR, the part we can't explain. Now let's look at the part we can explain. To do that, we now need to calculate out our grand mean. Now notice here that there is only one grand mean, and it's the same one all the way down because there is only one, 4.24. Now to calculate out our between group variation, that's the part we can explain, we have to take our group mean and we subtract it from the grand mean over here. So it would be 4.04 minus 4.24, and then we would square that, and that would give us our variation. So that's our between group variation. So we get that number there, and we sum all of that up, and you'll notice down here that then we have a total between group variation of 6.5. So it's almost 50-50 split between the two. The percentage that we explain is almost 50%. All right, so finally, just so we can make sure that that comes out the right way, what's our total group variation? And our total variation should be our grand mean here and our individual ratings. And so our individual ratings, then, we just subtract the one from the other. And 3.8 minus 4.24, and that gives us our total variation of our data. And that number here is going to be 12.51. And if you add 6.02 and 6.5, you're going to get 12.51. Correcting for rounding, they're exactly the same. Okay, great. So we figured out our estimations for our variance. But what do we do with that now? Well, we do what we did with linear regression. We put it into an ANOVA table. When you do linear regression, you take those results and you put them in the ANOVA table. You do one-way ANOVA, you put them in the ANOVA table. Same thing. And you'll see here that the chart is virtually identical to the one that we had for linear regression. The only thing we changed is that instead of SSE and SSR, it becomes between and within. Now, the only other difference you have to be aware of is the number p, or in this case, our degrees of freedom p right here. That p value, when it's linear regression, is the number of estimators you have. Now, actually, this is still the same thing, but we haven't been talking about estimators. We haven't been talking about regression lines. So what this is here is this is just the number of degrees of freedom of your estimate, P, in one-way ANOVA is the number of categories. So in our example, the number of categories was 3. Maybe you only have 2 if it's a gender thing. If it's male and female, those are 2 categories, right? If it's high or low, those are 2 categories. It's just however many categories you have, that's what P is. And then you go through and you calculate your ANOVA table exactly the same way. So let's go and do that. All right, we're going to work across like we did before with our linear regression. We're going to put in our numbers for our between, within, and total. So there's what we calculated out. Our estimate's 6.5, our residual is 6.02, and our total is 12.51. And we go across. Now here's our degrees of freedom. We had 3 categories, so P minus 1 is going to be 2. Our total number of degrees of freedom, we have 15 participants. So that gives us 14 total degrees of freedom, and the difference between the 2 for the residual is 12. Then we figure out a mean square. Dividing 6.5 by 2 gives us 3.25, and then 6.02 by 12 is 0.5, and our total there, that's just our variance number there under mean square. Then we find our F value, which is going to be 6.5, and that gives us a p-value of 0.01. And so that is definitely significant. We need to be under 0.05, so that's a significant rating. And like we said, our R squared is just about 50%, right? Right around there, so that's pretty good overall. Okay, so that is how you do one-way ANOVA. That's it. That's all there is. But I want to take a look at it. I keep saying it's exactly the same thing as linear regression. So I just want to spell that out so it's very clear how it is the same as linear regression. Now, one-way ANOVA using linear regression. Now, most typically, now remember, our linear regression, we're trying to come up with an equation that's y equals, as you know, mx plus b. Or in statistics notation, it's y hat, our model estimate, equals beta 1, our slope, x1, plus beta naught, which is our intercept. So that's the model we're trying to fit into. Now you would think that, okay, so we have this general equation here. This is just the basic general equation for one variable. Well, in our example, we have one variable, right? We've only got a set of groups. Our groups can be 1, 2, or 3, right? So we can put group 1, group 2, and group 3. This kind of makes intuitive sense to you that you would just use the x variable and put in 1, 2, or 3 because that's really simple. Unfortunately, that's not the way you can do this. You can't just put in 1, 2, or 3 for the variable. That would mean that if I had 50 categories, I'd still only have one variable because I could go 1 through 50. I could have 1,000 categories. I'd still only have one variable, one independent variable. And that's not what we want, because that's not true. We have many different categories, so we have many different independent variables if we had 50, 100, 1,000 different categories. So our model has to reflect that, and we have to be able to differentiate those different categories more than some arbitrary 1, 2, 3, 4 scale. All right, so the rule as to how many independent variables you need is simply the number of categories minus 1. So however many categories you have to subtract that. Now in our case, what that's going to mean, we have 3 categories. Remember, we had no extracurriculars, non-physical extracurriculars, and sports. In our case, that's going to mean that we have 2 independent variables, x1 and x2, because 3 minus 1 is 2. All right. So now, this also explains why our degrees of freedom. Remember, our degrees of freedom for the estimate was p minus 1, and we said that p was the number of categories. That's what we said about the ANOVA table. So that's actually what it is. We're doing the exact same thing. So here we've got 1, 2, 3 estimators. So that's why the number of estimators or the number of categories both works out. So here we've got 3 again, which would have been if it was linear regression. So in both ways of thinking about the degrees of freedom, you're going to come out with the same answer no matter which way you look at it. But here, the important thing for this is that we need to code our answers or our variables in a way that reflects the complexity of how many categories we have. Now, finally, we know that we have these X variables, X1 and X2, or 3, 4, depends on how many categories you have. But we have these X values, and we know we can't just give them any arbitrary value like group 1, group 2, group 3. So how do we go about coding those variables so they're representative of the categories that we're using? Well, there's two ways to do that, and I'm going to go over the first way completely and then look at the second way. That first way is called dummy coding. All right, dummy coding only uses zeros and ones. So let's take a look at an example of this in the case of two categories. If you have two categories, then that means you only have one independent variable that you're using. And so it's very easy to code for just two groups. You make one group all zeros, and you make the other group all ones. And that gives us that nice even split that we're looking for. So any participant that's in group 2 gets ones, and anyone in group 1 gets zeros. And that's it. Very straightforward, very simple. Now, it gets more complex as you add more categories and more X variables. So what we're interested in, and now here's the example of 3 categories, we have 2 X variables. What we need to make sure that we have clear is that the combination of the 2 X's are not the same. So what I mean by that is here for X1, it's 0, and then X2 is 0. So we represent group 1 for the case when X1 equals 0 and X2 equals 0. For group 2, we represent this as when X1 is 1 and X2 is 0. And then for group 3, this is represented when X1 is 0 and X2 is 1, the reverse. And so this is how we do dummy coding. And now this is why you need an independent, the number of categories minus 1 equals the number of independent variables, because that's the minimum you need to be able to represent these different categories using only this zeros and ones system called dummy coding. All right, so we've got this 0, 0, 1, 0, and 0, 1. What does that do for us when we're looking at it? Well, what that means is that if we look at our equation, that beta 2 x2 plus beta 1 x1 plus beta naught. That beta naught is a line intercept of your typical y equals mx plus b. It's that intercept. Like what happens when this x here is 0? When that x is 0, well then y just equals the intercept on a line like that. So in the case where we have a group that we set as 0, 0, that means that when we're talking about group 1, that means that our intercept, beta naught, or in the normal algebraic way, b, is going to equal the group mean of the control. And so what we mean by control is that if we have everybody knows what an experimental control is. That's the group you don't alter. That's the group you don't do any experimenting to compare all the other groups to. So the control group is the one we would assign the 0, 0 to, as the one that was unaltered and we didn't do any experiments with. So if your experiment calls for a control group, you would most likely use dummy coding so that the intercept was equal to the group mean of the control. And that makes it easier to compare what happens when you do have what they call a treatment group and an experimental group of x2 and group 3 or whatever it happens to be. So use dummy coding mainly when you have a control group. Now, on the other side, we're going to look at the next way of doing the coding, and that's called effect coding. Now, effect coding uses positives and negatives. And so I'm going to explain what that means in a second. So the goal is to balance out our positives and negatives. So here's an example of our 2-category system like we had before. But instead of using 0 and 1, we're going to use -1 for group 1 and +1 for group 2. Now here, we're going to see, so we have 4 participants for group 1 and 4 participants for group 2. If we were to add down this side here, we were to add all 8 people together, we're going to get 0 because we have 4 negative ones and 4 positive ones. That's one of the necessary elements of effect coding, is that the sum of the column has to equal 0. So that means there's a lot of way to weight the different groups in different ways. And so you can actually look at it in a number of different ways. Now here's an example, another example of two categories where you don't have the same number of people in each one. In group 1 we've got 4 participants, but in group 2 we've only got 3. But we still have to have a total of 0 down here at the bottom. So what that means is if I make x1 -1 all the way through, that's going to be -4. And so this group 2 has to sum to be +4. So that's why it's 1.33. So we need that balance between the two. It always has to sum to be 0. Sum is always 0. That's what effect coding is. So this is another way. You can do it both ways, dummy coding or effect coding. It depends on what you're looking for. Like I said, if it's dummy coding, it's primarily when you have a control group. You don't always have a control group. So this is for a different type, which we're going to talk about in a second. But first, let me show you the example of 3 categories. So here's an example of 3 different categories. So here I've got x1, and our group 1 is defined as 1 and 2. So whenever x1 equals 1 and x2 equals 2, that is representative of group 1. If it's 0 and 1, that's representative of group 2. And if it's -1 and -3, that's representative of group 3. All right, now, if you look here, the sum of the columns, right here, if we go down, we have 4 1s, 4 0s, and 4 -1s. So that also sums to be 0 all the way down. On the other hand, x2 is also going to sum to be 0 because we have 4 2s, which is 8, plus 4 1s, which is 4, for a total of 12. And then we're going to have -3 times 4, which is going to be -12. So that still adds to be 0. Now that's a very strange weighting of those values, but it could be conceivable that maybe you want to look at it that way. Now, effect coding is used when there is no control group and you're really just looking at how the different groups compare with each other or compare with the average of all your data. So the intercept in this case, so again that y equals mx plus b term right there, or that the beta naught over here, that is not equal to the group mean, and instead it's going to be equal to the grand mean, the sum of all of your data. And that comes about because all possibilities added together for x1 or x2 is 0. So it ends up balancing out and you end up with an intercept that's equal to the grand mean. And so whenever you're interested in a set of groups that deviates from that grand mean, and you want to know why are these groups deviating from the overall mean, that's when you would use the effect coding. All right, so that's how you do it in the linear regression form. That's everything you need to know. That's how one-way ANOVA is related to linear regression. Now, you don't have to do linear regression when you do one-way ANOVA. I showed you the procedure for doing it without the regression, but I also showed you the way to do it with the regression. So you can choose which is easiest for you. Usually that's the one-way ANOVA if you have categorical variables, but it's up to you. All right, so that's it for your last statistics lecture. Thank you for listening through all 7 of these. Thank you for being in the class.
That's all, folks.